Hi friends, we are going into class 1 of module 4, Automatic Generation Control. So the power system operations which were considered till now was under the steady load conditions. That means we didn't consider the cases where the load is changing. But when the load starts to change or the load demand changes, both the active and the reactive power starts to the demands continuously changes. The active and the reactive power continuously changes. So what is needed is we have to control two main things. One is, that means the active power and the reactive power is to be controlled, and this is to be done using two main control methods. One is the controlling the input, and the second one is the controlling the excitation. So normally the input of the turbo alternator is used for matching the active power. Otherwise what happens is the speed will increase, or it may vary, and it will be going out of the permissible limit. The frequency will go out of the permissible limit. The speed and frequency are directly related, so the frequency goes out of the permissible limit. Second one is the excitation control. The excitation control is done to match the reactive power. Otherwise what happens is the voltage will at various system buses goes beyond the permissible limit. So these are the two controls used for controlling the whole system. That means according to the change in the load demand, the active and the reactive power is controlled like this. Active power is actually controlled using the input, and reactive power is controlled using the excitation. Okay, this topic we have already studied in our synchronous induction machines. I will be just showing you the topic. Effect of change in the prime mover input. What have we studied in synchronous induction machine is, if we are connecting two alternators in parallel, then what will happen if there is a change in the prime mover input? You can see it here. I am just reading the conclusion of it. Thus, an increase in the prime mover input of generator 1 causes the real power shared by it to increase, and a corresponding decrease in the real power shared by generator 2. So, what does it mean? If you are increasing the prime mover input, then what happens? The real power shared will be increasing. That means the active power will be increasing. So, input increasing, then the active power will be increasing. Similarly, what about the effect of change in excitation? If you are changing the excitation, what happens? Two alternators which are connected in parallel, and what happens if you are decreasing the excitation of one of the alternator? So, I will just read the conclusion of this. The decrease in excitation in generator 1 causes the reactive power shared by it to decrease, and corresponding increase in the reactive power shared by generator 2. So, what does it mean? It means that if we are changing the excitation, if we are decreasing the excitation, what happens to the reactive power? That will be also decreasing. So, these two are the effects which we have already studied in our synchronous induction machines, and using the same concept it is being explained here. So, input is controlled for matching the active power, excitation is controlled for matching the reactive power. Now, coming to the main system, that is automatic frequency, load frequency and excitation voltage control. In the modern large interconnected systems, the automatic generation and voltage regulation equipment is mainly installed on each generator. Why? Because a manual correction of this frequency and voltage is not possible. So, it is an automatic method, automatic frequency controller and voltage regulation equipment is used on each generator. So, this is the schematic diagram of the this is the complete schematic diagram of the load frequency and the excitation voltage regulator. So, I will just describe regarding this schematic diagram. So, what all things are there? You can see there is a turbine and there is a generator. The turbine and the generator, they are coupled to each other using with their shaft. Okay, and the input to the turbine is steam, and to the generator an excitation is given, that is an excitation coil. This is an excitation coil, and an excitation coil is given. Now what is done is we are taking two feedbacks. One is the frequency feedback and the other one is the voltage feedback. The total power which is given by the generator is P plus JQ, and the load voltage and load frequency is noted. So what is done? Let us go through the first one, that is frequency. So the load frequency is noted and it is given to a frequency sensor and a comparator, and where it is being comparing with the reference frequency and a value or signal is being produced. This signal is given to a steam valve controller, and this steam valve controller gives the command to the input whether to increase or decrease the input steam. Okay, so this is how the feedback of the frequency side works. Similarly, how the voltage controller is doing its work. The voltage of the load is given to a voltage sensor and a comparator, and this is again given to a excitation controller where the excitation is being controlled. So what happens if there is any change in the voltage, the compared value, it produces a signal, and this is given to the excitation coil, and by which it can increase or decrease the excitation, thereby controlling the voltage. So what is done? The voltage as well as the frequency is being controlled using two different loops, or two different feedback loops. Okay, the figure shows the load frequency and excitation voltage regulators of a turbo alternator. So the controllers are set. Now how it is being designed? It is designed for a particular operating condition, and they mainly take care of very small changes in the load demand without change in frequency and voltage. That means without the frequency and voltage exceeding the prescribed limit. It should be inside a particular limit. So it will take care of all the small changes in the load demand without the frequency and voltage exceeding the prescribed limits. Okay, so next one is what is load frequency. Now this load frequency and excitation voltage controllers, they both are non-interactive. What does it mean? If you are controlling the frequency from one side and controlling the voltage from the other side, frequency from one side, and if you are controlling the voltage from the other side, both are non-interactive. Okay, some reasons are given in the textbook. You can go through that. There are some reasons why they are saying that both are non-interactive. Why the load frequency, the frequency control and excitation voltage control both are independent. Some reasons are given. You can go through it, those who need a further study. Now, changes in the load demands can be of two types. Load demand can vary two ways. In two ways we can say, one is slow varying changes and the other one is a fast varying changes. The slow varying, the regulators are normally designed for to be insensitive for the fast random variations, whereas they will be sensitive for the slow varying changes. That means the regulators are designed for mainly to work for the slow varying changes, but they neglect the fast random variations. Why? Because otherwise it will be subjected to hunting. All those such random variations will be taken into consideration. So only the slow varying changes will be considered. So that's all for today. So that is this is the first introduction class. In next class we will be going for each of the control. First we will go for load frequency control, then afterwards we will be going for the automatic voltage control. So thank you, and I hope you understood.